So the idea is that if we have a virtual model, okay, like we say some model of my field, and I can try to produce it in different ways, okay, that allows me to find the best way to, to produce the actual asset, the actual field. So I'm going to make here, usually a field in a very simplified way has a few elements, okay? Field, let's say field schematic. Okay, first I have a hole in the ground, where I have the reservoir, right? That's my reservoir. Okay, inside that reservoir, inside that well, I have a pipe. Okay, that's, yeah, the surface can be the, in this case, if we are talking, it's a seabed, or it can be the platform. Okay, let me make it maybe with that color. Okay, and then I have then I have here, I'm going to make, just, I have a set of valves, okay, that you don't have to see for now, but these are valves that we use in a well, okay. But then you have one main component that is an adjustable valve, okay. Let's make it painted like that, okay. That is an adjustable valve, okay. All of the others, I'm able to open, or either open or close, okay, all the others that I have here. This valve is an adjustable valve that is called a choke, okay. And then I have my pipeline. Typically I have some section of pipe, and then I have finally the separator. Okay, so we have three components: reservoir, well, we have this choke, control element, and then we have this pipe. Okay, those are basically the main elements of my field. I can have many wells, I can have many pipes, I can have many chokes, but those are what I have to look to find the performance of my field. Yeah, so if we make, so just be careful, okay? Here I'm saying it reaches a separator and that's it, okay? And that's because here I have a pressure, right? Reservoir pressure. And here I have another point where I have separator pressure. So between these two is that I have the flow. And this separator pressure typically keeps constant during the life of the field, okay? For some mechanism. Some mechanism, advanced control, level control, and pressure control, is making sure that that pressure is always constant, okay? But be careful. Here you have this limiting capacity that you have to take into account, okay? You can block it. Just analyze your system from here to there, okay? But you have to always be careful with the maximum capacity of oil, gas, and water. Always, okay? Even though you don't include it in your model. So this system, let's make first, for those of you who are not petroleum engineers, let's make a mechanical analog okay, of a field, okay, of the field. And the mechanical analog, I'm going to say first, the reservoir is going to be a tank, okay. In a very simplistic way, it's just a way where I have a storage of fluids, oil, gas, and water, and I made a hole in that tank, okay, and I'm producing that fluid. Okay, so that's my reservoir here. Now, on the well, to go from that point where I have reservoir pressure to flow towards the well, okay, I have some pressure losses, okay. Actually, the flow is driven by this pressure difference. Here, the pressure at this point that we are going to call PWF. What is the name of that pressure? flowing bottom hole pressure, okay? I need them to be different to have flow, okay? So to represent that pressure drop, okay, I'm going to put just like a restriction, okay? And that restriction is fixed, okay? It usually shouldn't change. It's not something I can I can modify, but not something that you should modify. So as is flow, this restriction is due to flow information towards the wellbore, and I have here this point that is PWF. Okay, so these two, the tank and this restriction, they are representing the reservoir system. Okay, one is the storage and one is the pressure drop towards the wellbore. The next point, what did I have next on my system? I go up, right? And the next point is the well. Okay, this pipe that I have taking from -3 kilometers on the underground all the way to the surface. That might be seabed, might be platform. And that I also represent in the same way, okay, like a restriction. And this is flow in tubing, okay? And this point here, how is it called? PWH, that's wellhead pressure. Okay. So how can I change, just, a small detour, how can I change this restriction in the tubing? If I change the pipe size, right? I use a smaller pipe. The reservoir, this flow information is not so simple, but I can add something that makes easier the flow. That's something can be acidizing, fracturing, something like that. Okay, so I could in principle change them, but it's not that they change. It's not that something I can do every day. Okay, something that I have to put a lot of effort and time and money to do it. What is the next point? I have the choke, right? And then I have a pipe that we can make it like that, the flow line, and then I have a separator, which will be simply a condition of constant pressure. Okay, actually I shouldn't make it close maybe, because then there will be accumulation, but I have something like this. Okay, and it's almost stupid, but it helps you to so let's say I'm operating the field in plateau mode. Okay, what do you have to guarantee to do that the field will be operating in plateau mode with this system? Here we're going to put a pressure gauge. Okay, we're going to be monitoring pressure. What happens with time when I take material out of the reservoir? What happens with PR? It's going to decrease, right? So the flow through the system, okay, here we have QO or Q gas. It depends on, so Q oil is a function, okay, of PR and P separator, among many other things. It is a function of that pressure difference. So with time, that guy is going to go down and down. Okay. So what can I do to keep the rate constant? A control engineer, okay, what would be the solution of a control engineer? Okay, we can make the control engineer say easy. I can make the control engineer looks at what can I control? He said, well, this guy here, right? I can control this thing here. Okay, this valve. So I can put here a rate, that will be rate to measure rate, okay, flow rate meter. I put here some input to a control system, okay, and that goes to that valve. And I actuate that valve such that I keep the rate I keep the rate constant. Okay, so that tells you here that depends on also the choke opening. Okay, it depends on the pressure upstream, it depends on the pressure downstream, but also it depends on the restriction I have on the choke. Okay, so intuitively, if pressure goes down with time, okay, reservoir pressure goes down with time when I start to produce. Okay, what do I have to make to keep the rate constant? Okay, to keep the same Q. QO. Okay, to keep this rate constant. I have to add more pressure drop or less pressure drop. If you have this system, right? If you want to, okay, if you don't do anything, let's say you keep the choke at the same position, okay, and you just leave that system go by itself. How do you think the rate will go? Just simply down, right? Because what we were saying, the rate, if the choke is open, then the rate simply will go down, okay? Why? Because PR goes down, and then the difference between PR and P separator becomes smaller and smaller, and then you're going to get less rate, okay, with time. Now, let's say I want to produce this rate constant, okay? That was the rate, open choke, okay? What do I have to do to produce this rate at that time, 0? I have to choke, right? I have to create a pressure drop, okay? Remember, it's a function. The rate is a function of PR, of P separator, that I cannot do anything about it. Okay, these two are, one is going to go down, one is going to remain constant, but of the delta P of the choke, okay? How much, and the delta P depends on the opening, okay? How much is the choke open or not? So to produce that rate, I have to add a pressure drop, okay, due to the choke. So the choke has to be like partly closed, okay? Then in the next time here, what do I have to do here? Reservoir pressure went down, okay? And then I have the same choke, is very close. Therefore, if I do nothing, the rate will also go down, okay? So what do I have to do? Open the choke, okay? So if you make this plot, you want to keep a constant uh, rate, okay? Then the choke opening will be the opposite, okay? Let's make it maybe with red. No, actually it will be a choke opening from small to big, okay? So what happens with time? If I start opening the choke, opening the choke, opening the choke, I reach a point where the choke simply is fully open, right? And what happens then? The end of the plateau. Okay, so that's in our case, in our very simple analog, our very simple tank, very simplistic tank system, we're saying that the end of the plateau will happen when, you know, the choke is already fully open. I start with the choke closed and I start opening and opening and opening. If you want a plateau rate, this number, I cannot have plateau, okay? Already the choke is fully open, okay?
So next to our tank analog, this mechanical analog, I put this the more realistic this drawing of the production system, and I have also marked the same important points. You have reservoir pressure, you have flowing bottom hole pressure, then you have after at the top of the tubing you have the flowing wellhead pressure, and then I have put here this point which we call the production downstream the choke, and finally separator pressure. So first is the flowing bottom hole pressure is sometimes abbreviated as BHP, but we prefer to use the ESP, SP nomenclature, which is big, small p, WF in subscript. But it can be also, you can see this tag in many simulators, bottom hole pressure. And then you have the flowing wellhead pressure, which we use the small letter P and then subscript WH. But it also, you can see it's also used as WHP, wellhead pressure. So the flow from PR to PWF, we typically represent this flow with an equation. This represents the flow or the pressure drop that I have in the formation, all the way when the fluid goes through the porous media, all the way to the bottom of the well, to the sand face. And this I typically use, so that's what we call the drawdown, that delta pressure drop. And we represent that with an equation that we call inflow performance relationship. And it's an equation I'm going to put here, simply a drawing how it looks like, but it's an equation that relates the rate, and be careful here, the rate that I'm relating to is the rate at standard conditions. I have used here G as a gas as an example, but can be also oil, as a function of that reservoir pressure and that bottom hole pressure. So in a way, I'm removing out, I'm taking out the effect of time. I'm saying in this, although this system is dynamic, PR is changing with time. So I'm saying at a given time, for a given reservoir pressure, I will have this equation. When this PR is changing, let's say going down, if I have depletion, so then I will have the effect on of the time will be somehow captured by this PR. The equation looks a bit like that if I'm plotting here the rate at standard conditions and the bottom hole pressure. It looks a bit like that, and let's see if we make sense of this plot. So when we have no rate, this is 0. Okay, that means that I have here simply, if it's a horizontal, if I have here, I say these 2 points are more or less at the same elevation, so then I will have simply reservoir pressure. Okay, so at 0 I have here simply reservoir pressure. To erase it here on the side. Then I just copy again and move it down. And then if I reduce that pressure, that means I'm reducing this pressure by some means, then I will have simply the rate will start to increase. From 0, it will start to increase to a maximum. And really, if you think about what physical bound I have on the pressure, bottom hole pressure, you might say this will be atmospheric pressure, what I managed to reach here. Okay, although in reality it's not the case, because I have to overcome some losses all the way to the surface, but we could say theoretically I can go as low as atmospheric pressure. And this flow rate usually is called absolute open flow, AOF, what the formation can deliver, okay, what the well can deliver. Then we continue on our cold current. That means that the flow is going on this direction, and then I'm going on the direction of the flow from the bottom of the well all the way to the top. And the next part I have, it's a flow in a conduit. Essentially I have the flow in the tubing. Okay, I could have might have flow like it looks here a bit in the casing, and then I have flow in the tubing. But essentially, to keep it simple, let's say we just have flow in the tubing. Now we have So that's the flow in the tubing, and this equation we are going to call the TPR, the tubing performance relationship. And again, it's a relationship I have depending on what's the delta P, or what's the pressure here and the pressure here, it gives me how much rate I will have. So you see here I call it a function tool, and I say it's a rate at standard conditions of oil or gas, and it's a function of these two pressures, the flowing bottom hole pressure and the flowing wellhead pressure. And we are going to look later a bit more in detail how that looks like for multi-phase flow, but if we consider the case of single-phase flow, either oil or gas, let's make we can draw it like this. Okay, so you have, if you're plotting, you're keeping somehow constant the pressure here. Let's say it's connected straight to a separator and the choke is fully open, and the separator has a system to regulate the rate. So this pressure is kept completely constant. Then for zero rate, okay, let's say you have, and here will be zero rate, gas rate. The pressure that you're going to get at the bottom, and here I'm keeping this pressure fixed, and I'm neglecting the rest of the system, just looking at the tubing and not assuming there is any formation. So the pressure I will have here will simply be the hydrostatic pressure. In this case, if I have a gas, it will have some hydrostatic column of gas, and then finally I reach that pressure. So that's the pressure I have here. It's not exactly separator pressure, but it's something big. Okay. Then as I start increasing the rate, I have flow rate through this tubing, and it's still keeping the same pressure fixed. I will see that I need more and more pressure, more than the hydrostatic, to flow through that tubing. Okay, because now instead of, in addition to having to overcome these hydrostatic pressure losses, I also have to overcome the frictional pressure losses that occur when the fluid is moving inside the pipe. So that's why if you see the diagram, keeping wellhead pressure constant, and if I increase the rate, I need more and more pressure to overcome those frictional losses. Okay? If I had no rate, then it will be simply the hydrostatic column, and when I'm flowing, I need more and more, okay? Depending on how big the rate is. So that's the case for considering liquid. Let's say you're single phase undersaturated oil, or if you have dry gas. But if you have multi-phase, the curve looks slightly different, and we are going to see exactly how it looks like. But at this stage, I just want to take into account that this is from PWF to a PWH is another equation I need to use, and they have some logical relationship that looks a bit like that. Okay? If I keep this pressure fixed, I have to increase this pressure with the rate. When I increase the rate, I have to increase the pressure. And now let's go to the next big pressure drop in my system, which is from flowing bottom hole pressure, flowing wellhead pressure to the discharge of the choke. And essentially here what I have is a pressure drop across a restriction, across very small channels, very narrow channels over which the fluid has to pass, and that causes losses. So that equation I call the choke equation. And if I could represent it somehow, it will be the Q of the gas as a function of flowing wellhead pressure, the discharge pressure of the choke, but also here I have something that I can regulate, that I can control. In the previous cases, in the tubing, I had nothing usually that I can control unless I have artificial lift, and in the inflow also not something that I can control to regulate the rate. So, but what I have here on the choke is something that I can move up and down, that I can regulate. So that's the case that I have opening, and the rate is a function of these three. Now we're not going to cover yet the equation of the choke because we don't need it yet. Okay, I'm going to cover a bit more in detail later. But usually what I have to say is that these models are highly inaccurate. are usually inaccurate because it works okay with a single phase if you have either undersaturated oil or water and gas, but if you are starting to have multi-phase flow, they're usually inaccurate. They are also highly nonlinear, so they bring a lot of issues when I'm trying to solve the system of equations, when I'm trying to find the rates and I'm trying to make this calculation. They are nonlinear. They are sometimes also difficult to converge when I try to converge the whole system, and I have also many options from which to choose. There are many models that have been published, and each company usually they have some preferred model that they use depending on the case. So because of that, we're not going to go too much in detail in choke modeling, but we are going to find an alternative approach that I'm going to discuss later. But essentially, if you see here, it's a nonlinear ugly equation that relates these two pressures, that relates the rates that go through the choke, and also relates the opening of that choke. Okay, for example, if you have certain rate and I have full open, I will achieve some downstream pressure, but if then I increase the rate with the same upstream pressure, then and reduce the opening, I will have a lower pressure downstream the choke. Okay, so it's the pressure, if this one is constant and the rate is constant, the pressure downstream depends on the opening of the choke. The last part on that trajectory of the fluid is from the downstream of the choke to the separator. I have a section of pipe that could be, in this case I have put a very simple pipe section, but it could be a subsea network. The collection of pipes that commingle the production from different wells can be a riser going from 1,000 meters in the subsea to the top side. And this model is actually similar to the tubing model. Okay, you have an equation in which is, of course, the relationship is a bit different, but it's a relationship between the rate that goes through that pipe, the pressure into the pipe, and the pressure out of the pipe. Very similar, and the same philosophy applies. If I keep the pressure at the end of the pipe constant and I increase the rate, then the pressure at the inlet of the pipe should be higher. The pressure that you need is going to increase with the rate. So this equation I call the pipeline or flow line performance relationship. Okay, FPR or PPR pipeline is for when you are commingling large amounts of oil or gas and you are sending to the top side, to the platform. And flow line is our minor flow lines that take the production only from one well or a few wells to a pipeline, to a main pipeline. Okay, so production scheduling, if you remember, was to plan and predict the production rates with time, okay, of the field. And we say will be of the three main phases, right? Will be oil, gas, and water. But essentially, there is one which is the field is either an oil field or a gas field, and that will be the one that I will be controlling and looking most closely. But also due to bottlenecking, all kind of other things, design of the facilities, I want to compute the other two. Okay, if it's gas, oil, and water, oil condensate because it gives me this extra revenue that can change the economy of the field, and water because simply it causes a lot of issues in the plant. Okay, and also oil, the same thing. Oil, I want to calculate gas. Maybe gas simply re-inject, don't get any revenue out of it, but it will cause some changes in the design of my separator, my compressor station. Okay, and water, the same thing. Okay, so I'll say production profiles, which are or maybe we can say, in a broader sense, we can say field performance. Okay. We want to see how the field, because the idea, remember, in the design phase is we have tried to create a synthetic field. Okay, we have a real field there. We are not sure about all the details of this reservoir that we made, but we want to make like a surrogate. We want to make an image, okay, which now you will call a digital twin, okay, in this era. But you try to create a digital twin and you try to produce it in many different ways and try to see which one is the best. And finally, when you do that exercise, you see which one is the best. That's the strategy that you apply in your real field, okay? In the real field, you have one shot, no more than that, okay? But in the digital twin, in this model that we have, we can do it many, many times and see which one is best, okay? So production profiles can be estimated or are typically estimated with, and there are a few methods that some of you, or I guess most of you, will be familiar with. And one of the preferred methods is with Reservoir Simulator. Okay. You try to represent which Reservoir Simulator essentially I'm trying to solve. It's a model that tries to make first a 3D representation of my volume that I have, of my all the properties, all the parameters. I okay, try to make a 3D representation of my volumes. Okay, then I start to subdivide those volumes. Okay, and then I apply conservation equations, some sort of mass conservation equation between each block. Okay, each block has a certain amount of fluid, certain amount of pressure, and then to compute the flow, what is transferred between one block and the other, you use some sort of Darcy law, okay, with permeability. The main thing with reservoir simulation is that you need some, so typically you have some boundary conditions which are, you try to represent the aquifer, right? So you include the aquifer sometimes in that simulation. But essentially, all the other external boundary conditions are usually no flow. Okay, you apply simply nothing is flowing in and out. Okay, I try to represent the whole volume. Unless there is a fault, communication with the neighboring reservoir, but usually you try simply to say the block and I have no flow coming in and out through the external bounds. Okay, but you have some boundary conditions in some cells which are the wells. Okay, that's where you're saying that's where I'm going to produce. I make a hole and I make a condition on that particular cell, that's where I'm going to be draining fluid. Okay? So for those of you who are versed in reservoir simulation, okay? So what kind of conditions you specify in these wells that I have here? If you remember from anyone had a course on reservoir simulation? Yeah. So what kind of condition do you specify on the well?
Valve pressure, bottom hole valve pressure,
Mm-hmm.
and also flow rate.
Okay. You specify basically two things. Okay. You specify something that is called a target rate. Okay. Either of oil or gas. Okay. But QT. And that's how much I want to produce. If I will be at plateau rate, simply that will be the rate that I want, the fixed rate that I want to produce with time. And the second is you specify a minimum bottom hole pressure. So the simulator first will try to say, I try to produce that rate, okay? And actually we will see it operates slightly different, but I say if I cannot produce that rate, simply I switch to this minimum bottom hole pressure. Okay, I operate at a constant bottom hole pressure. Okay, but I try first, the simulator will try to produce this target rate. Okay, and then it's fine. If I can produce it, will be fine, but if not, then change to minimum pressure, and it's typically bottom hole pressure. Okay, and this minimum bottom hole pressure is supposed to represent the things that we were discussing last lecture. Okay, it's supposed in the reservoir simulation we are just basically simulating up to that point. Okay, the formation, the kind of the storage effect, and we are simulating also this kind of flow from here all the way to here. Okay, that's essentially what we are trying to capture. Okay, so I have to represent all of that system in the reservoir simulator. I have to put a pressure that I think has to be enough to go from this point all the way to the facilities. Okay. Okay, but of course that pressure we will see now is actually changing with time. That pressure that I need is actually not a unique number, but it's something that will depend on rate. Okay, how much rate, how much water do I have, how much so that's like a simplistic approximation, this approach here. It will depend on how big the rates are, you know, how much gas, how much water do I have, how much oil do I have. Okay, it will depend on these things. So a workflow that we use in typically or in field development to compute, and here the main thing is realistic production profiles. Okay, so we have typically the guys which are the reservoir engineering. Okay, where you have usually a 3D reservoir model, and in that model I compute is based on Q target rates and PWF mean, okay, that they assume, and sometimes that can be also changing with time. Okay, and also the Q rates then can be changing with time. But they make their analysis. They start to, for example, so I have some plateau rate, I fix some rates, and I use some minimum pressure, okay, that I have used maybe before in other projects, depending on the water depth. They have some rule of thumb, and they basically say, well, I run, and from here I obtain my Q, okay, my production profile. Okay. Then you have another department, which is the department usually is production engineering and facilities production. That these guys have is a production simulator. Okay, production simulator basically is a steady state, okay, simulator. The reservoir is by nature is transient. Okay, so that simulator has to take care of what happens in time, while this one can simply be a steady state. And then they check at each point in time is this QT feasible? Okay, That means if I will be able with that Q and PWF that I record, okay, with time, is that going to be enough to reach, okay, here we have, will that feasible, and feasible here means the separator. Okay, so they go and check with this value and the PWF with time that they have sent. They go to their model, steady state, and each point in time they go and check, is it enough to reach the separator? Okay, and they sometimes they might take measures to try, so they try to make it feasible. Okay, either by changing tubing size, either by including artificial lift, either by maybe changing, doing some, for example, gas lift. They try to make that rate. They might to be. They try to make that rate simply that it can work. Okay, because supposedly reservoir engineer, they are applying those rates because they lead to higher recovery factors. They have some objective why they are using those rates. Okay, so they lead to high recovery factor. They lead to high revenue. They think that these are the best rates. Okay. Okay, and then you have a feedback loop where you flag some years where it's not possible. Okay. Okay, simply you say, according to production engineer, they say, well, in years, I don't know, from 10 to 15, you won't be able to produce that rate. Simply, it's not enough to reach the separator. Okay, so they give back that feedback to the reservoir engineering department, and the cycle starts again. Okay, and there is usually a fight between them because the reservoir engineers say, let production take care of that. They will find a way to produce it, and production say, no way, I cannot produce that, and there is some iteration. Okay. Okay, but take in mind the guys in the left, they are the custodians and they are the managers and they are like the owners of the reservoir model. Okay, and the guys on the right, they are the owners of the production model. Okay, they know all the details about the facilities, the sizing, the wells, everything, and they have to simply communicate. Okay, because the production profile is actually a result of both. Okay, if we look again at our analog, is the result of this part, which is very important. Okay, it has a significant effect to model that part and to understand this part on my production profile, but also this part. Okay, we should never neglect the importance of this part. Okay, and of course, if you are at a very early phase of field development, probably this part is the reservoir model. I have a very crude and very primitive model, but I have something, right? Based on seismic, based on geology, based on petrophysics, based on something. But these guys usually, if you're at the very early phase, you have no idea how the well will look like, what kind of diameter I'm going to need, the trajectory of the pipe, for example, at the bottom of at the sea bottom. So one assumption that is typically made, simply I compute production profile simply using the reservoir model, okay, without taking into account the facilities. So let's put that comment here. Okay. And as they are neglected, you see that has an impact. This process is actually very important to see that those rates are going to be feasible. Okay, so it is not done because it doesn't exist, this model, or I don't have any idea how I'm going to produce it. It actually causes some inaccuracy in these profiles that I calculate. Okay, if my reservoir engineers made a good job at predicting this minimum bottom hole pressure, it might be over predictive, under predicted, or it might be spot on. Okay. Yeah. So you use reservoir simulator. Some improvement that has been made now in these late years is that people use reservoir simulator coupled with a well gathering network simulator. Okay, and we're going to see now a bit, maybe what the word coupled means. But basically, I try to join these two models such that all predictions that I calculate already take that into account. Okay, I try to take out the middleman. Okay, this might be a manual process. It happens through emails, through meetings, sending information manually, and it can be very time consuming. That department takes a few weeks to generate these profiles. Then that department takes also some weeks to verify those rates, and then they have to send back their comments. Okay, so to avoid that time delay process, simply they try to couple these models in. This is typically called in a IAM software. Okay, IAM stands for Integrated Asset Management. Okay, so let me just write here some examples of reservoir simulator. We have one of the most famous is Eclipse. You have CMG. You have the new version of Eclipse, which is Intersect. Okay, what else do we have? Nexus. What else? Petrel, but that's not really reservoir. Okay, that Petrel is for the geo modeling. You have also kind of MATLAB, MRST. You have now this OPM, Open Porous Media. You have a sensor. Okay, some companies, they have their own simulator. Aramco has powers and gigapowers. I think Chevron, they have their own simulator. Okay, and these guys, the production guys, what do they use? Okay, we have PipeSim. We have Prosper and Gap. Some people use Olga, which is by Schlumberger also. I think there is a program called PipeSoft. There is one called from Weatherford or Rio. Okay, but essentially there are two different programs maintained by two different departments, even by different company, and you want to put these two together. So here you have some platforms for integrated asset management. Resolve is one of them. You have Avoset. You also have one pipette from a company here in Trondheim, which is now Tieto. Okay. But as I told you, that might be challenging, especially in early field, because you need to have a model of this part which might not exist. Okay, there is a big uncertainty around it. What kind of well size, how spread are going to be the wells, what will be the topography of the seabed, what will be exactly the water depth, what is separator pressure, for example. Okay, the sizing of the lines. All of these, they require a lot of engineering work based on information that is not available at that point in time. Okay. Other options I can use to estimate production profiles.
Material balance.
Material balance, but usually material balance is not enough. I have to have what I call an IPR equation, inflow performance relationship. Okay, so material balance, this guy tells me how pressure, how saturations, okay, of gas, oil, and water are going to change versus time, okay, or depending how much I'm draining for that volume. That's what material balance is. Instead of having all of these blocks that I make here to subdivide the volume, I simply make a big block, okay, and then I say all of that is going to change uniformly. When I take out some amount of oil, some amount of gas, that's how these variables are going to change. Okay. And then on top of that, I need some IPR relationship that tells me what is the relationship between rate as a function of reservoir pressure and bottom hole flowing pressure. Okay. So this guy comes from the material balance, but this guy here is actually an assumption. So then I have to make an assumption on PWF. Okay. So needs assumption on PWF minimum. Okay. So still I need this minimum. Okay. Another approach, which is a bit more advanced than this one, is material balance. Okay, material balance, remember, is a tank, single tank, a reservoir simulator, and then you have material balance plus a well and network model, in which I couple these and I do my calculations exactly the same way, but here I have Q has a function of PR and P separator. Okay. Okay, I include my model, doesn't include only up to the bottom hole, but also includes all the way to the separator. What other things do we use to calculate the rates?
Darcy.
Darcy, which is like IPR. Okay, I use some sort of. Okay, I use some. We will see now a bit about. For those of you who are not familiar, we will see kind of have a crash course introduction to IPR. Okay, but essentially it's a relationship that tells me if I apply this drawdown in the well, how much rate I'm going to get. Okay. Also, something that is very much used in the US is some sort of decline curves, okay? Decline or type curves. That I simply say I have some decline in time of wells, okay? Typical declines. It might decline like that, it might decline like that, it might decline like that, okay? And I say, based on experience, this particular reservoir is similar to another one we produced before, and it had this type curve decline. Okay? It's very simplistic. I try to group by categories, wells, and then I try to make a field based on some combination of these wells. Okay, let's say I will have 30% will be good producers, they decline in this way, then 30% will be bad producers, and the rest will be medium producers. Okay, and that's something I make either for example in the onshore planning, but I typically use it in very early phase. Okay, at least in Norway. Okay, so the main what we are going to use in our course is going to be this approach. Okay, because simply it's slightly easier to make exercise based on this approach, and also you are including both important parts to calculate production profile. Okay, so we are going to be focusing on this particular case. No, sorry, in this case, material balance and well and network model. Okay, but we are going to make, I'm going to give some comments on decline or type curves. How are they related somehow with the other approaches, and what is people try to do with this decline? And we are going to give some comments about the coupling. Okay, how, if you use that approach, what kind of coupling, what is happening in every time step. Okay, which is a bit similar of the way we do it here, that coupling, but you get slightly different information from the reservoir simulator. Okay, that clear, more or less? Okay.